for the training thousands of students to date.
Wow.
It is educators like you that truly make a difference in this world and who will inspire the next generation to propel humankind on future missions to Mars and beyond.
This is too much.
For me, it's become a way of life, and I'm just so thankful to everyone for what it's done for me. I just want to share that with my students. Maybe it'll inspire them to reach a little deeper or to go a little further or maybe to try a little harder, whatever it is in life.
The International Space Station is the most fantastic vehicle ever built.
It's a one-of-a-kind laboratory orbiting about 250 miles above the Earth.
And we perform experiments on the International Space Station.
We can do science, we can do experiments, we can learn how to do things out of this world. And the result will help benefit the people on the ground.
Space station really provides an opportunity to explore, for example, say medical applications.
The aging and the osteoporosis and muscle wasting conditions are greatly accelerated in microgravity.
The weightless environment will give us insights into things like diabetes and maybe even cancer.
Understanding those phenomena allow us to look at how we can improve treatment of disease here on Earth.
If we wouldn't have conducted experiments on the ISS, we wouldn't have known that you could use cold atmospheric plasma in such broad application areas we're now exploring.
One of the most promising results has been gained by studying a protein associated with Duchenne muscular dystrophy.
We may be able to slow the disease by half, potentially doubling the lifespan of many of these DMD patients.
We provided iServe imagery for many natural disasters, including floods and fires, for deforestations, for volcanic eruptions, and for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
This was when we realized we had a chance to make a difference in the world using the same technology that was used by NASA, but applied in a remote area of a developing country.
I think it's made people much more aware of the issues of water quality. That's a very powerful thing.
Having the HyCO on the International Space Station has been the ideal test bed for our research.
We can monitor these water bodies from space, and if we can reduce exposures both to humans and even animals, then we've achieved our goal.
And now today, we're able to operate the largest fleet of Earth imaging satellites in human history.
And none of that would have been possible without the International Space Station.
The space station has done so many things for life on planet Earth. It shows us what human beings can do working together. It shows the science that we can discover.
Over 2,000 experiments have flown on board ISS. 170 countries around the world have participated in some fashion, either in the ISS itself or in one of the experiments. Our rate of research is actually increasing. We're doing more today on board the space station for research than we have ever done before, and that's only going to continue in the future.
And so what we're seeing today is a proliferation of new ideas and new concepts. It's almost like it's a renaissance of what's happening in space. Buckle up and strap down, because this is going to be a rocket for all of us in the global community to be part of.
Carroll Township's a very rural area in northern Ohio, right on Lake Erie. Lake Erie has always been very important to Carroll Township and its residents. We use it for drinking water, we treat it, and it's really our livelihood.
In Lake Erie, for what unknown reason, suddenly the toxin level spiked, and that got through the treatment system.
It was indicated to me that it is pretty dangerous.
Cyanotoxins can cause skin rashes,
headaches,
nausea,
vomiting, stomach problems,
nervous system problems,
liver damage,
to death.
We sampled, and we had about 2.5 times the limit from the World Health Organization. The second sample was approximately 3.5 times. Our
plant wasn't set up to handle what was coming in from Lake Erie. One of my biggest worries was actually hurting someone or even worse. So we shut it off right away, shut everything off. We had a very close call that day. The last thing you want to do is produce an unsafe water and allow your people to drink it. What we need is a better way to track and predict these cyanobacteria entries from our source water so that we can make sure that this never happens again.
A lot of the times we'll find out after the fact that there's a problem with cyanobacteria in the water because the bloom's already occurred. We either get results of sick animals or sick people. We need a paradigm shift. We need to go from being constantly reactive to these blooms to having a capability that allows us to become proactive. And the U.S. Environmental Protection Agency has been very encouraging of allowing for some high-risk, high-reward projects. And that allowed us to think outside the box, way outside the box. We've been fortunate enough to make use of a sensor on the International Space Station called HICO, which stands for the Hyperspectral Imager for the Coastal Ocean.
HICO consists of two instruments. One is a camera, and the second instrument is a spectrophotometer, which actually gives us the spectrum of light leaving that water.
The camera on a cell phone, for example, contains about 3 bands of data in a red channel, a green channel, and a blue channel.
HICO gathers light from the red, orange, yellow, green, blue, indigo, and violet parts of the spectrum. So using this technology, we're able to now detect those water quality parameters such as water clarity, what the phytoplankton concentration is in your water, how much light is being absorbed in your water, as well as what's the distribution of cyanobacteria in those waters, and does that concentration pose a health hazard?
So what this means is instead of waiting for someone to report that there's a problem with cyanobacteria bloom, we can monitor these water bodies from space
and get information that we can rapidly get out to the water quality managers through a smartphone application that we've developed.
So the app allows you to drop a pinpoint, and that pin can be placed in an area where a drinking water treatment plant may have an intake, and see what the current water quality conditions were. Each user gets that information near real time, so they can make judgment calls on whether they have to respond or take action.
Having the HICO on the International Space Station has been the ideal test bed for our research.
This is an amazing partnership. The Naval Research Laboratory had HICO on NASA's International Space Station. As HICO acquired a scene, it was transferred to the Naval Research Laboratory. And then the Environmental Protection Agency was able to do the analysis and the validation to send this information out through a prototype mobile application. Yes, this technology will reduce costs and provide near real-time information. But the big goal here is protecting humans. And if we can reduce exposures both to humans and even animals, then we've achieved our goal.
As farmers and winemakers, we work very hard to grow the best quality fruit possible to make the best wines possible. The real polished part of winemaking is letting that wine age gracefully so those flavors can be preserved and brought to your home and to enjoy in the glass. The greatest issues we face as winemakers is that our optimal storage conditions for our wines are also optimal growth conditions for mold and bacteria.
Mold is really bad in a barrel room or in a cellar because it has an odor to it. And the wines are a living, breathing thing. And actually, they pick up the characters of where they're living.
The wines can absorb that aroma, and it's just not a healthy environment to work in. My father and I built this barrel room underground. The challenge is we've got some stagnant air which can cause mold growth. Who knew that our solution would be not underground, but up in the sky?
In order to carry astronauts to Mars for deep space exploration, you have to be able to grow your food stores. You don't have enough space and capacity to carry them with you. So NASA began experimenting with growing crops in space. What they found is that in the growing chambers on the International Space Station, the crops they were growing were emitting a naturally occurring hormone called ethylene. It's a gas, and ethylene is the reason that fruits and vegetables ripen.
But the problem was, in space we're going to have a very confined environment, so the ethylene concentration can build up, especially in a plant growth chamber. It basically destroys the plant. And so there was a need to grow plants in space, and we were good at growing plants here at the University of Wisconsin. And so NASA came to us and said, we've got a problem. I think you've got a solution. Can you help us?
Through the University of Wisconsin Advanced Astroculture Program, they developed an ethylene removal system that was successfully tested on a number of missions on the International Space Station. So the ethylene removal system that was developed draws air through a reaction chamber. The air is passed across a catalyst bed, and that catalyst has the effect of removing anything organic from the air. That includes mycotoxins, bacteria, viruses, and even mold.
It showed us that with the right technology, we can overcome the challenges of growing plants in space and enable future space explorers to grow their own food as they continue to explore the solar system.
The International Space Station program not only supports the technology that allowed us to get rid of ethylene in the Space Station astroculture program, but it also provides a great variety of technologies to exist that otherwise wouldn't have been possible.
Realizing that this technology could have tremendous benefits here on Earth, we developed the Aerocide air purification systems. Initially used in the perishables world for prolonging the shelf life of fruits and vegetables, not long after that, we realized because of the effects the technology has on mold, that the wine industry was a perfect complement for the technology.
This technology has been a real boon to us. It helps me sleep better at night.
But as you can see around the cellar, there's not a lot of mold.
Within 24 hours, the amount of airborne mold spores were dramatically reduced.
Within 2 weeks, about 99.9% of the mold had vanished on the walls.
It solves problems before they occur.
The room smelled fresher. It actually enhances your storage conditions for you to even make better wine.
It's really amazing when you think about all the innovations that are going on up in space, how they can come into a place as unexpected as a winery, which translates into benefits on your dinner table.
SERVIR is a joint NASA and USAID program where we're working with developing countries around the world and strengthening their ability to use satellites to address the many problems that they have, including floods, fires, harmful algal blooms, and other types of events that they have where they can use satellites to really make better decisions.
We're using space information to help decisions that affect people in the village where they live.
When there's a major disaster, governments around the world come together and they provide all of the satellite data basically that the world has to offer. But there's smaller disasters that occur in the countries that we work in that may not make the front page of the New York Times, but in that country it's a really big deal. We asked ourselves, could we make a difference if we had a dedicated imager for acquiring imagery quickly after natural disasters and to be able to provide that imagery back to the countries that need them, that have real decisions that need to be made with a very quick turnaround. As NASA, we looked in our own backyard and started thinking, could we use the International Space Station? The International Space Station was a really fantastic asset to take advantage of because it passes over 90% of the Earth's populated area every 24 hours. We developed an imaging system and we called it iServe, which basically is a camera and a telescope system that sits inside the International Space Station and can collect imagery when it passes over natural disasters or other events that we need to collect imagery.
Initially, we were planning to take few pictures per day.
So we contacted all the USAID missions around the world, and in total we had more than 2,000 requests coming, for people who need images from iServe.
And we moved to like 1,000 images per day.
We provided iServe imagery for many, many natural disasters, including floods and fires, for deforestation, for volcanic eruptions, for earthquakes. So it was really a fantastic example showing how imagery from the International Space Station could be used in these times of dire need.
And now we have a huge archives of images of areas around the world.
iServe is an
So this is
example
something that
of,
was not
in essence,
really there
making the
before.
International Space Station is an example of, international, in essence, making the International Space Station to village to better understand and protect our home planet. And connecting space to village to better understand and protect our home planet.
NASA Marshall Space Flight Center is Science Central for the International Space Station. NASA Marshall Space Flight Center is Science Central for groundbreaking research in microgravity. Our team have supported more than 3,400 investigations from around the globe. We have supported more than 3,400 researchers, commercial companies, and even students to expand scientific discoveries on the orbiting laboratory. And even students now to expand scientific discoveries on the orbiting laboratory. Now let's hear how each flight controller position is critical towards making science happen in space.
Welcome to the Payload Operations Integration Center. As a Payload Operations Director, I manage the day-to-day operations of science experiments performed on board the International Space Station.
The science experiments on the International Space Station range from studying human physiology to dark matter and even growing plants in space. As a payload rack officer, our job is to monitor and ensure the safe operational use of these experiments.
It's very important that tools and parts are safely organized on the International Space Station. Every day, stowage engineers track the location of these items so astronauts can easily find them to conduct science experiments.
The PACOM team talks directly with the ISS astronauts, guiding them through science experiments and technology demonstrations. The crew are our system, and we advocate for them from the ground.
Analyzing, integrating, and communicating. These are the responsibilities of an operations controller. We ensure that the astronauts have the resources they need to complete their science experiments safely.
Sometimes even the best plans need to change. Timeline change officers work with NASA centers and scientists from around the world, developing the best plans for each science experiment.
It is important that science data is transmitted down to Earth. As a data management controller, I help to ensure that data from Space Station is sent to scientists around the world.
The Marshall Ground Control Team ensures that all ground equipment is fully operational, such as computers, servers, hardware, and software. We also make sure that all data is successfully sent to and received from the satellites.
Thank you for visiting. We hope you've enjoyed this behind-the-scenes look at how Marshall enables scientific discovery.
We've all seen The Martian, and we know we need breathable oxygen to survive on Mars. What's up, Watney? It turns out it's a lot better to be able to extract it from the atmosphere of Mars, then bring it with you on the trip over, if you have the technology. Let's see how close we are on this episode of Crazy Engineering. I'm here with Jim. He's going to teach us how to get oxygen on the surface of Mars. Jim, can you tell us where we are right now?
Absolutely. This is the JPL Mars Oxygen In-Situ Resource Utilization Laboratory. We call this the MOXIE Lab for short. The MOXIE instrument is a demonstration mission designed to prove that we can produce pure oxygen on the surface of Mars. If it's successful, NASA may opt to send a dedicated mission to produce oxygen for humans to use in the future.
So how do we make oxygen on the surface of Mars?
It's actually a fairly easy process. Basically what we do is we take Mars atmosphere, we run it into a unit called a solid oxide electrolysis unit, which is basically a fuel cell in reverse.
Wait a second. Reverse fuel cell? How does that work?
So this is the solid oxide electrolysis unit. What happens is we have Mars atmosphere enter in this line, goes into the SOXY unit. It's then heated up to 800 degrees Celsius. We inject energy into the cathode and anode. And then what happens is oxygen is separated from the CO2 and comes out this line over here. This line here is the waste gases that's left over from the catalyst process.
To test this technology, you're going to need some Martian atmosphere. Where on Earth are you going to find that?
We know the composition of Martian atmosphere. It's 95% CO2 with some trace gases. And there are companies here on Earth that will mix that gas for us. We call it Mars mixed gas, and we use it for most of our testing.
Well, what if we land on top of a mountain or down in a valley? The conditions for extracting oxygen are totally different. We've got to test for all of that.
So the way we test for it is we design an instrumentation system that covers all of the conditions of the instrument. Lower pressures, higher pressures, clogging filters, oxygen purity, all of that stuff.
Why don't we just bring the oxygen with us when we go to Mars?
It's very difficult to bring something from the surface of the Earth to the surface of Mars, and it costs millions and millions of dollars. So it's much easier and better for us if we try to get that resource from the planet.
Well, it's obviously a huge challenge, but we're both really optimistic up here. We're excited to see it on the Mars 2020 mission. Check back soon for some more crazy engineering. Heads up, Watney.
All engine 50 years ago, we pioneered a path to the moon. The trail we blazed cut through the fictions of science and showed us all what was possible.
It's very pretty out here.
Today, our calling to explore is even greater. To go farther, we must be able to sustain missions of greater distance and duration. We must use the resources we find at our destinations. We must overcome radiation, isolation, gravity, and extreme environments like never before. These are the challenges we face to push the bounds of humanity. We're going to the moon to stay by 2024, and this is how.
This all starts with the ability to get larger, heavier payloads off planet and beyond Earth's gravity.
For this, we designed an entirely new rocket.
The Space Launch System. SLS will be the most powerful rocket ever developed.
And with components in production
and more in testing,
this system is capable of being the catalyst for deep space missions.
We need a capsule
that can support humans from launch
through deep space and return safely back to Earth.
For this, we've built Orion.
This is NASA's next generation human space capsule.
Using data from lunar orbiters that continue to reveal the moon's hazards and resources.
We're currently developing an entirely new approach to landing and operating on the moon.
Using our commercial partners to deliver science instruments and robotics to the surface, we are paving the way for human missions in 2024.
Our charge is to go quickly and to stay, to press our collective efforts forward with a fervor that will see us return to the moon in a manner that is wholly different than 50 years ago.
We want lunar landers that are reusable,
that can land anywhere on the lunar surface.
The simplest way to do so is to give them a platform in orbit around the moon from which to transition.
An orbiting platform to host deep space experiments and be a waypoint for human capsules. We call this lunar outpost Gateway.
The beauty of the Gateway is that it can be moved between orbits.
It will balance between the Earth and Moon's gravity,
in a position that is ideal for launching even deeper space missions.
In 2009, we learned that the moon contains millions of tons of water ice.
This ice can be extracted and purified for water. It can be separated in oxygen for breathing or hydrogen for rocket fuel.
The moon is quite uniquely suited
to prepare us and propel us to Mars and beyond.
This is what we're building.
This is what we're training for.
This we can replicate throughout the solar system.
This is the next chapter of human space exploration.
Humans are the most fragile element of this entire endeavor, and yet we go for humanity. We go to the moon and onto Mars to seek knowledge and understanding and to share it with all. We go knowing our efforts will create opportunities that cannot be foreseen. We go because we are destined to explore and see it with our own eyes. We turn towards the moon now, not as a conclusion, but as preparation, as a checkpoint toward all that lies beyond. Our greatest adventures remain ahead of us. We are going.
We're going.
We are going.
We are going.
We're going.
There is orange soil. Well, don't move it till I see it. Hey, it is! I can see it from here. It's orange. Wait a minute, let me put my visor up. It's still orange. Sure it is. Crazy. Orange. I've got to dig a trench, Houston.
Fire emergency. We got another fire. Can you find anybody that could come in and help us?
But we had no visual of which fires were burning where.
We have to learn from this. We can't tolerate this level of damage, this many deaths.
The key factor now is how can we make use of our NASA data?
To see the fire we're fighting, we use the NASA MODIS satellite system.
Okay, copy that.
To be able to put in instrumentation ahead of a real wildfire is almost impossible to do.
There we go.
One of the basic tenets of NASA was to study the Earth, study the home planet. So fire is an important role player, whether it be with the atmosphere or the environment and its effects on vegetation. So fire just becomes a natural subject for the study of Earth processes. NASA data and NASA modeling efforts and NASA science capabilities, which derive from our satellite orbital assets, and allow us to basically cover the full spectrum of fire, from predictive analysis, active fire monitoring, to post-fire rehabilitation and recovery.
It was a normal night, and then my phone rang at 12:30, and it woke me up. You could hear the wind howling.
I started getting texts in the middle of the night, people asking me if my parents were okay. About 2 a.m., I get a text from my boyfriend who was out of town, and he said, "Are you okay?"
Fire medical dispatch. County train state of fire, go ahead.
We see a fire in the distance in the Napa Hills, just north of the city of Sonoma.
We have a report of a tree and house on fire. So I called about 10 minutes ago. There's a house on fire right next to the house we're staying in.
I'd smelled smoke, went out on the front porch, and the sky was glowing orange and bright. The wind was blowing like 40 or 50 miles an hour, and the fire was close.
Vegetation fire, City of Calistoga, Highway 128 crossing Tubbs Lane.
911 fire emergency. We got another fire.
Okay, I'm sorry. We can't even take the calls anymore.
Can you find anybody that could come in and help us? Anybody. All hands on deck. All hands on deck.
I was the division chief in charge of central operations in the Sonoma Lake Napa unit. One of my responsibilities was the oversight of the 911 dispatch center. As I drove into the command center, I passed numerous fires on my way in. I arrived, and for the next 30 days after that, I never left.
The Tubbs fire basically started late evening between 8:30 and 10 p.m. on a ridge between Napa and Sonoma County, the wine country of Northern California. High winds were blowing from northeast to southwest. We call those Diablo winds. Some of the modeling that was derived from our Landsat data and micro-terrain relief modeling indicated that the winds at the summit were blowing over the ridge at almost 90 miles per hour, with sustained gusts above 70 miles per hour. The fire started from the downed power line or a transformer that was affected. And then with these 90-mile-an-hour winds, there was no way anybody was going to control that fire. When it got into some of the more developed urban communities, such as the Coffey Park area, because of the configuration of the winds blowing through that cityscape and the angular momentum created by the building structures, we created these fire whirls or fire tornadoes, which therefore burn or have speeds of up to 200, 250 miles per hour, burning through the community. So that's even pushing fire even hotter and into this urban environment that's composed of building materials, chemical agents in people's garages. So it wasn't just being sustained by vegetation burning at that point, it was being sustained by structures burning in progression down the fire line.
Our intelligence for the Tubbs fire was all based on the 911 reports we were receiving and the radio reports that we were getting from our fire resources and our law enforcement officers out in the field. But we had no visual of which fires were burning where or the magnitude of the incident. When we started getting reports of houses on fire in Santa Rosa, we couldn't comprehend that that could be the same fire that was burning in Calistoga because of how quickly that fire burned. And if we had had a bird's eye view, some kind of imagery so that we could get a picture of exactly what we had, that would have been a game changer. We're actually using some of the National Guard's manned and unmanned aerial assets so that we can practice the surveillance of our fires.
Testing. That aircraft and gimbal line of sight.
One of the major things that we have them help us with is some of the perimeter mapping and determining the exact location of our fires.
You ask almost anybody what California is known for, and it's either California burritos or wildfires, one or the other. A system we heavily rely on is the MODIS satellite system that is provided by NASA that does hotspot detection on the Earth's surface. And we use that to see in near real time where those hotspots are of that fire that we're fighting.
Okay, we got it.
And then we bring in track data and other layers to basically build that combined picture.
That's it? Yeah. Okay.
First responders, they want to know which houses have been damaged as quickly as possible. And the smoke may or may not have been cleared. But using radar, we can see where those houses are and where we maybe need to focus our efforts based on how a wavelength might bounce off of the surface. We can actually see through smoke and clouds. We can see things like vegetation structure or building structures.
We're going to support the North Ops, South Ops for fire season, which we're now pretty much defining like April to New Year's Day of next year.
We'll have a pretty good idea what the fire's doing early on, like on the campfire, where it starts so quickly and you see what's in front of you, but you have no idea what it's doing anywhere else. Like, that's where we can come in and provide a much better picture. And so I have NASA MODIS and VIIRS stuff, which we always use on Google Earth. You can kind of see the streets here. This is a neighborhood totally burned down. And CAL FIRE, they weren't used to being able to see through the smoke. The perimeter was right here, and they see right here there's a raging fire. They know the fire is now way out there.
Remote sensing is really important for the mapping of those incidents, and then also to help us figure out where those hot spots are.
We're outside of our 30-mile limit. We've got a fire out of our right wing towards the north.
CAL FIRE, go ahead and report it.
Prior to having the capability, we would draw by hand basically where the fire perimeter approximately was. Now, with the MODIS data being pulled in, we're able to see irrefutably where that fire was last known to be.
So look, here's what it looks like. So here's
remote sensing application has been a game changer in allowing us to see real time where our fire is. So our operations folks are able to make tactical decisions real time based on where our fire truly is.
Our primary objective is structure protection and just trying to stop the spread of the fire into the adjacent houses.
Looks like hundreds of homes possibly.
Hundreds of homes. We just got here this morning. I can't even give you a number.
There was a second phase where when the winds died down, we continued to have a more typical fire event, which was driven largely by the fuel loading in the landscape. As a result of the work that we did in collaboration with NASA, we were able to really separate those two events because we had really good data about wind levels and the time.
Our plants have been affected by years of drought. It means that we have years of dead fuel buildup in the state. It's called fuel load, and it's basically how much plant material there is within a specific area. And as that continues to increase the amount of fuel loading, our fires burn hotter and more intense and quicker.
It's in the relationship between topography, fuels, and climate that drive a fire across the landscape. The heat generated from the fire, especially in steep terrain, is what's propelling these fires forward. And then you add to it a growing wildland-urban interface, we are seeing just more impactful fire events and hence the increase in megafires.
The key factor now is how can we make use of our NASA data in the recovery operations?
We need to understand why some people lost their homes and other people didn't, why some watersheds burned. We need to understand the intensity and the damage done by the fire.
Seeing now.
So this is the post-fire imagery?
Matching up with what we're seeing now, a lot of this area within our view was burned.
So what was the fire direction? We're looking at it here. I mean, kind of from this direction, burned down and...
The fire started down in the canyon.
Okay.
And it actually burned to the east.
Right, okay.
And then the wind shifted and this part of the canyon burned in the topography-driven fire later on.
Okay.
Yeah.
After the fire burned, we needed imagery right away to understand the damage. Because now, several years after the fire, a year and a half, there's a lot of regeneration. If you have ladder fuels, that's the fuels from the ground up to the canopy. If the ladder fuels are dense, the fire's going to burn hotter, you're going to have more damage. And with LiDAR imagery, now we understand that.
So the way that LiDAR works is it will tell you the distance from the sensor of each point return. So when you send out a pulse and you get it back, you know exactly the distance that it traveled. And if we did that with billions of points, we can actually recreate three-dimensionally all of the structures in a space. We can construct the vegetation, we can even construct to the leaves on the trees.
A fire that burns through an ecosystem will start out as a ground-based fire primarily, burn up through vegetation communities and get into the crowns of trees. That's called ladder fuel development, which leads to a greater chance of very high severe wildfire.
We can now map the ladder fuels and where they occur across the landscape. Then we can compare where they occur next to homes or hospitals or roads. And with those things together, we can prioritize treatments for fuels. So we're going out of this study really well armed to be able to manage fire risk across the landscape.
After the fire, when I drove through the Coffey Park neighborhood, which was a half a mile from my house, the thing that struck me was how much it looked like images of Hiroshima and Nagasaki during World War II. All that were left were standing chimneys, brick chimneys. Everything else was totally consumed, burned to the ground.
We've been using wildfire as a tool for millennia. We've been using it for cooking, to grow crops and nutrient cycling. So we've had this relationship where fire is a tool, but at the same time it's also a natural disaster, right? We don't think of hurricanes as tools.
I had revelation that prescribed fire was an important part of restoring ecosystem management over about the last 10 or so years, and we need to make it a consistent part of our management of our resources. Introducing prescribed fire into that ecosystem allows us to remove some of those underlying ladder fuel components and allows that forest floor to kind of open up and not have the propensity to burn in dramatic wildfire style.
This is part of a very large project that's called the Fire and Smoke Model Evaluation Experiment, and it's as close to a wildfire as you can get. The objective is to collect a suite of data to both evaluate and advance our fire and smoke models. To be able to put in instrumentation ahead of a real wildfire is very dangerous and almost impossible to do.
NASA founded our previous project that actually allowed us to build, this prototype with the fire model. It's focused not just on the prescribed burns, but also on wildland fire. We were able to get, the new forecast run just, before the briefing, and just right after the briefing we get the first results. So we had an idea about the wind speed, rain.
Winds aloft are going to be start to crank this afternoon, so there's going to be a sweet spot early this afternoon.
So what time are they thinking of igniting?
So this part of the unit over here, we're looking at around 1300, 1400, letting the sun get on it. This is our one concern area where we have continuous fuels. We're going to send the hot shots that are rolling out of here right now.
We see all the valley over there. We should be in a good spot to set up our truck in the LiDAR. That's gonna be a more intense burn, but also the plume should be going this direction, so we will be able to really have a good angle.
Right here, and then transition is gonna be the...
I think we have so much better chance, for the fire to take off and kind of start moving, freely after the ignition. So from that standpoint, it's gonna be, really interesting.
Air temperature, 65.4.
Attention on the crew net, attention on the crew net. The helicopter is airborne and they are igniting test fires at this time.
So topographically of where they're going to go push and drop another barrel of gel is in a slot canyon right back over there. And so it should follow this, maybe be over it, but we'll be underneath and be able to watch it just go right over us. Cool. So.
smoke. So I think we'll get something out of it.
We had to move back up the hill here to clean air while the column folded over on our location there.
So I'm super happy. I kind of believe that our forecast, it was really spot on in terms of how strong the winds are over this region. The same in terms of the plume location. I mean, you see that we are actually really close to the plume, and that's what we wanted. 5 years ago, when we were talking about real-time coupled fire atmosphere forecasting, and people were saying that, well, that's impossible. 5 years later, I mean, we have completely different computational power, to execute, those forecasts. I mean, we can really do that.
That's really the takeaway message for this whole program, is that he was able to initiate his model today and yesterday and get a forecast that matches what we're seeing.
So I'm super happy that NASA had a faith, in this whole idea. It's great, to see that, running, working, and I hope that, pretty soon, other people will be using that, and it will be very helpful in designing prescribed burns, but also, in terms of fighting wildland fires.
This is the home site right here. This was the garage right here, and then you can see the patio in the back. The fire was coming from the northeast. Once it hit that stand,